Hello and welcome in. In this video, we're going to be looking at our intermolecular forces, the specific forces that we might encounter that end up dictating the properties of our substances. We said we're always thinking about this balancing act between how much energy our substances have and how strong our intermolecular forces are. Here, we're going to be looking at that second part. How strong are these intermolecular forces based on our molecular structures? So intermolecular forces, these are the forces between one particle and its neighboring particles. So we're always going to have to draw at least two of these atoms or molecules. Here we're looking at the forces that exist between one hydrogen chloride particle and the neighboring hydrogen chloride molecules. This is different than intramolecular forces, which might be chemical bonds. In general, these intermolecular forces are really, really weak. We're considering these very weak forces that are orders of magnitude or an order of magnitude weaker than our chemical bonds, but still act to determine the properties of our substances, such as melting point, boiling point, vapor pressure, enthalpy of fusion, enthalpy of vaporization, and many more. All right. So let's go through these types of intermolecular forces one at a time, starting with our weakest of our weak forces and building up to the strongest of our weak forces. So our weakest intermolecular force is known as London dispersion forces, or perhaps just London forces, also known as van der Waals forces. Now, for these London dispersion forces, we said they are the weakest. And as it turns out, every single atom or molecule will display some amount of these London dispersion forces. The way that this works is we have some instantaneous dipole that might appear in our molecule, which can be attracted to other induced dipoles in the neighboring molecules. So imagine this molecule taking a picture of this helium atom at three different points in time. We have our nucleus in the center, and we have our electrons in this 1s orbital. At this point in picture one, great, there's two electrons on opposite sides of the atom, no problem. Picture two, yeah, same idea. These electrons are somewhere in this orbital. Picture three, well, yeah, also these electrons are somewhere in this orbital. But in this third picture, we have an abundance of negative charge on the left side of our atom and an abundance of positive charge at the nucleus or on the right side of our atom. This is a partial negative charge on the left and a partial positive charge on the right. This is known as an instantaneous dipole, just by happenstance at one moment in time, since our electrons are dictated by the probabilities outlined by our quantum mechanics. It just happened to have a small separation of charge throughout our atom or molecule. Now, this instantaneous dipole will interact with the molecules around it by causing induced dipoles. If our atom all the way on the right had a instantaneous dipole just by happenstance, the molecule next to it can try to shift its own electrons around to match that and to get this nice attractive force between the new positive charge it formed and the negative charge that just happened to show up on its neighboring molecule. Getting these negatives and positives to line up is beneficial. This is a nice attractive force, and it's what gives us this weak attraction between one particle and the ones around it. We can see why all molecules have London dispersion forces. The only requirements here are having electrons. Our electrons and our nuclei just might happen to be in a position where we have some instantaneous dipole. We can also maybe see why this is very weak. This instantaneous and induced dipole might be there for one moment, but there's no guarantee that it's going to stick around, and it might be gone the next moment. This is what we see as our summary, our weakest force based on molecules in close proximity, based on the polarizability of our molecule. Everything is going to have these London dispersion forces, but molecules that are more polarizable, where it's easier to shift around electrons, are going to have stronger London dispersion forces. This ends up corresponding to larger and heavier molecules having stronger London dispersion forces. As our molar mass increases, as our size and surface area increases, our London dispersion forces are going to get stronger. We can see this by comparing our halogens, fluorine, chlorine, bromine, and iodine. This is going down the periodic table. And just looking at the phases of these molecules, fluorine is a gas at room temperature. Chlorine is a gas at room temperature. Bromine ends up being a liquid at room temperature because we have stronger London dispersion forces. Iodine, as the largest, heaviest molecule here, has the strongest intermolecular forces and ends up being a solid at room temperature. We said the shape might also dictate the strength of our dispersion forces. So greater surface area, just like Velcro, also gives greater attraction between our neighboring molecules. So here are some isomers of C5H12, where we have different boiling points based on the different amounts of surface area. Smaller surface area means, well, weaker intermolecular forces, which will lead to lower boiling points, easier to boil. As we have more surface area, we'll have stronger intermolecular forces, and it'll be harder to boil, higher boiling point temperatures. Interesting fact, the way that some geckos are able to climb on trees or climb on walls is by manipulating the amount of London dispersion forces between their toes and what they're walking on. If you zoom in on this gecko toe, you can see tons of small features known as maybe setae. And on those small features are even tinier features called maybe spatulae, where their toes have an incredible amount of surface area, leading to a high strength for their London dispersion forces. So the stickiness here for a gecko's toes is strictly due to the amount of surface area, the surface contact they have with the wall or the tree that they're climbing. To step on and step off, they can adjust the amount of surface area and be able to walk on these slick surfaces. All right, moving up the chain, our second intermolecular force is known as dipole-dipole forces. These are going to be stronger than our London dispersion forces because the mechanism is based on permanent dipoles. If we have a polar molecule, we will have some negative side of that molecule and some positive side of that molecule. This is not just instantaneous, this is always there for polar molecules. When we have a partial negative and a partial positive, these forces can be attracted to each other. These poles can be attracted to each other. And so one molecule can be attracted to its neighboring molecule. Or maybe we can have a mechanism like this. Regardless, our interaction here is much stronger than our dispersion forces. And so we will have stronger intermolecular forces whenever we have polar molecules based on these dipole-dipole forces. Lastly, our strongest intermolecular force, the strongest of these very weak forces, is known as hydrogen bonding. This is a particularly strong intermolecular force where we have hydrogen bound to nitrogen, oxygen, or fluorine within our molecule. When this happens, we can have that hydrogen and nitrogen, or hydrogen, oxygen, or hydrogen, fluorine part of our molecule interact with a neighboring molecule. So let's be clear here. We're talking about the intermolecular force. So the force that exists between one molecule and a neighboring molecule. So if we have HCl, we saw that one earlier. We can have hydrogen bound to chlorine. Well, oh, not what we're looking for. What if we have HF? Okay, now we have hydrogen bound to fluorine. So we have this situation. We're going to have to look for actually the intermolecular force. How does this molecule interact with its neighboring molecules? And so we'll have to draw another HF molecule. And the hydrogen bond is going to be this weak force that exists between hydrogen on one molecule and fluorine, oxygen, or nitrogen on a neighboring molecule. The reason this occurs, and maybe does not occur with chlorine, is because hydrogen is a very small atom. Fluorine, oxygen, and nitrogen, also relatively small atoms. And the difference in electronegativity is very large between hydrogen and those atoms. And so we have really concentrated, really dense partial positive and partial negative charges on our hydrogen, partial positive, and our other atom, partial negative. And so we get a really strong attractive forces between these very dense areas of negative and positive charge. So in order to have this hydrogen bonding, we need to have, yeah, exactly that, hydrogen attached directly to an oxygen, to a nitrogen, or to a fluorine. And then our actual intermolecular force, this hydrogen bond, it's not a full chemical bond, but it's this weak attractive force that exists between one molecule and a neighboring molecule. And as we said, much weaker than a full chemical bond, only about 5 to 10% as strong. And there we go. Those are our 3 intermolecular forces. Here, notably, hydrogen bonding is what allows DNA to form our double-stranded helix and to have very high specificity between different DNA bases. So these 2 parts of our double helix are connected purely on hydrogen bonding between our different base pairs. All right, we can go through a practice problem here, decide the relative properties of our substances based on the types of intermolecular forces that might be present. So our strategy will be to identify the intermolecular forces on each of these molecules, and then compare which molecule has the strongest or the weakest intermolecular force. So we have London dispersion forces, we have dipole-dipole forces, and we have hydrogen bonding. For our first molecule, we have dimethyl ether. And so we can ask ourselves, well, do we have London dispersion forces? Well, yes, everything has London dispersion forces to some extent. If we want to know the relative strengths of these London dispersion forces, we can think about our surface area and our molar mass. For these compounds, they should be relatively close. Approximately equal dispersion forces for each of our 3 molecules. In order to have dipole-dipole forces, we need to have polar molecules. So is this dimethyl ether polar? You can add in the lone pairs that are not quite drawn on these molecules. And in order to decide whether something is polar or not, we need to consider, well, our Lewis structures, our Vesper geometries, and the relative polar bonds that might exist in our molecule. Here we have a polar bond between carbon and oxygen, a polar bond between carbon and oxygen, and this oxygen in the center has a bent geometry. And so this dimethyl ether, it's slightly polar. And so we might have some dipole-dipole interactions as these 2 dipoles on our molecule do not completely cancel. Lastly, we can consider hydrogen bonding. In order to have hydrogen bonding, we need to have hydrogen directly bonded to oxygen, nitrogen, or fluorine. We have hydrogen, but we do not have it directly attached to our oxygen. And so we do not have hydrogen bonding. Looking at ethanol, here we have a polar bond pointed towards oxygen, polar bond pointed towards oxygen. And again, we have this bent geometry due to these lone pairs. And so this molecule is going to be polar, and therefore we do have dipole-dipole forces. In terms of hydrogen bonding, we have a hydrogen, and it is attached to our oxygen. And so, yes, we will have hydrogen bonding between one ethanol molecule and the surrounding ethanol molecules. For our propane, we do not have any truly polar bonds. Carbon-hydrogen bonds are not very polar. And so we do not have these dipole-dipole forces. Likewise, we have hydrogen, but no oxygen, fluorine, or nitrogen. So we cannot have hydrogen bonding. So this is the list of intermolecular forces present on these types of molecules. The strongest intermolecular force is hydrogen bonding. And so ethanol, which exhibits hydrogen bonding, has the strongest intermolecular forces. Since it has the strongest intermolecular forces, it is going to be the hardest to boil. And so it will have the highest boiling point. And so, all right, 78.4 degrees Celsius as our boiling point for ethanol. Propane, which does not have dipole-dipole forces, is going to have our weakest intermolecular forces. And so therefore it will have our lowest boiling point. This will be the easiest to boil, negative 42.1 degrees Celsius as our boiling point. There is not that much keeping our propanes together. It's more likely to be a gas. And in fact, maybe we know that propane is a gas. This is what we use in our gas grills when we're grilling hamburgers. And all right, lastly, we have our intermediate intermolecular forces. Dimethyl ether is going to have a boiling point, maybe negative 24.8 degrees Celsius, somewhere in between ethanol and propane. Hopefully this has been a helpful introduction to intermolecular forces. Again, thinking about the relative strength of these forces in order to understand the properties of our substances. If you have any questions, don't hesitate to reach out. But otherwise, thanks for watching.